Yeah, welcome to this second lecture of module 1. It will be a continuation of your last lecture, lecture number 1. So, here today we will be discussing about the uniaxial tension test analysis. Though we explained about the flow stress flow curve and the instability in tension, which I did not complete. So, we find that in the stress strain curve, the engineering strain curve, the load during the uniform deformation, the load reaches a maximum value here, and then further that you will find that the load is decreasing, or the stress, engineering stress keeps on decreasing. And so, this it has a maximum value. Many times it is required to find out the maximum value, which generally corresponds to, which is nothing but it is the ultimate tensile strength of the material. So, this in real materials during the homogeneous deformation, it undergoes strain hardening, thereby increasing the load carrying capacity of the specimen due to plastic deformation. But this is opposed by the gradual decrease in cross sectional area of the specimen, and you will find that after it reaches this 0.3, the ultimate tensile strength or the maximum load condition, a localized deformation takes place, that is the onset of necking takes place at this maximum load, and then further loading you will find that further deformation you will find the load decreases continuously till the fracture point is reached, that is corresponding to point number 4 here. So, during this time you will find that so though from this curve it appears that okay, the stresses are decreasing, but in actual true stress true strain curve it will be continuously increasing. So, these are the condition we said. So, this is the strain hardening rate, it decreases, and maybe the true stress true strain curve now it increases, and at some point it reaches these two are equal. So, the condition we get, this also we discussed. The onset of necking is the case in the true stress in the engineering stress engineering strain curve, where the change in the load is 0, because it is initially increasing, then reaches a maximum point and then decreases. So, maximum condition is that dP is equal to 0, and the external load P is given by sigma into A, and we will find that this dP in the differential form we can write like this. So, it will give you this relationship dl by it should be dl by L is equal to minus dA by A is equal to d epsilon, and from this we can get this relationship we derived last day, d sigma by d epsilon is equal to sigma, that is the condition for the maximum load. Now, let us look at how to determine this value from a stress strain curve. So, the true stress true strain curve, the point of necking at maximum load can be obtained by finding where the subtangent is unity. So, because from the previous curve from the this derivation we can get this value, or the point at which the strain hardening is equal to stress, that is what we had to find out. So, that the stress whatever it be, that condition is coming, and by equation that using the engineering strain we can express the necking criteria as d sigma by d epsilon, that is equal to sigma. We can write it is equal to d sigma by d E into d E by d epsilon, because this is the condition where we are going to find out in terms of engineering strain. Okay. So, the previous case was for the case of true strain. Okay. So, in this case, so d sigma by d E into d E by d epsilon, that is equal to this we can write in this form, and finally, we will get that d sigma by d E is equal to 1 plus into 1 plus E is equal to sigma, or we can say d sigma by d E is equal to sigma by 1 plus C. That can be represented by, you have to do a little bit of iteration and find out okay, at what point this is equal to 1. Okay. So, and then draw a subtangent. Okay. So, such that this condition is satisfied. So, this is slightly difficult, a tedious job, because exact point you do not know where it is, it all depends upon how you shift that side or this side. Okay. So, that becomes very difficult. So, that is why in another case we can just find out it is d sigma by d E. If you just find out as per this relationship, d sigma by d epsilon is equal to this one, d sigma by d E into d E by d epsilon. So, that we can write it as d sigma by dE into dE is equal to dl by L naught and d epsilon is equal to dl by L. So, that we will get it as L by L naught into d sigma by dE. So, that is equal to, you get this equation, or from this it implies that d sigma by dE is equal to sigma by 1 plus E. So, that is very easy compared to the previous case, and this is called as a considerations construction for the point of maximum load. So, what we do is that from the 0 point, 0 strain, you take say a strain equal to minus 1 in the opposite direction, the negative direction of the strain axis, and with from that point you draw a line which is tangent to your true stress engineering strain curve. So, you are plotting the true stress versus engineering strain curve. So, from a strain value of minus 1, you just draw a tangent to this curve wherever it is meeting. So, that will be your the stress at maximum value. So, that see that is nothing but sigma u by, say here it is epsilon u you are getting. So, 1 plus epsilon u. So, that is the condition we are getting d sigma by epsilon. So, that is a slope which is equal to sigma by 1 plus E, which is the engineering strain. Okay. So, that is that way this drawing of this curve will be very easy to find out, and this is called as the considerations construction for the point of maximum load. Whenever you wanted to study the plastic deformation for computational purpose, because conducting an experiment initially, it takes a lot of time, and it also involves lot of money also. You need very complicated machines and other things. So, all these things comes into picture. So, it is many times for deformation studies always you go for some computational work, so that your amount of experimental work can be reduced. Okay. So, for that purpose many times it is necessary to represent the experimentally determined flow curve. Okay. So, you conduct a tensile test and get your flow curve, that is a true stress versus true strain curve. Okay. So, if you have that data for a particular material, normally what is done is that in the fully annealed condition where the material is soft, the people carry out that experiment, okay, do a tensile testing. And because during plastic deformation there is going to be say work hardening. So, you do not know when you are getting a material from the market, most of the wrought materials are subjected to plastic deformation, some are subjected to hot working condition, some are in cold working condition. So, in the cold working condition you may find that depending upon the amount of the strain or amount of plastic deformation we have given, so the its yield strength will be high when it is in the, especially when it is in the work hardening region or homogeneous deformation case. So, you do not know whether how much amount of strain has been given to the material, so that what will be the yield strength, you do not know about it. And not only that, in deformation studies, if you are getting, if there is a prior history of deformation, then all your calculations may get distorted based on the data which you are going to get it, because sometimes it might have been subjected to a high value that further deformation the material may fail, because there is a limit for the plastic deformation which is possible. So, all this information is required. So, in the normal case what people do is you take the material, maybe you might have got it from the market or locally purchased it, you do a fully annealing condition, so that the material becomes soft, there is no effect of strain hardening, the dislocation densities inside the materials are minimum, and so you can conduct, the material is very soft, in that case you carry out a tensile test. So, you get the exact representation of the stress versus strain plot from the data you are going to get it. And now, and this data will be used for further plastic deformation studies for analysis purpose. So, in that case you wanted this data to be represented in a in some form of empirical equations. Okay. So, this flow curve, and large number of people have come forward with different types of equations for fitting the curve. Okay. So, it is basically a curve fitting technique. So, one is the Holomon equation, where it gives that the stress sigma is equal to A epsilon raised to n, where n is the work hardening exponent, and A is called as the strength coefficient, sigma is the true stress and this is the true strain. Now, this was modified later by say Ludwig by the same Power law. He introduced the term yield strength in the initial case and other things, and then so this strain here refers to the plastic strain, not the total strain, it refers to the plastic strain. So, this can be represented by this. Swift has another form of equation. So, that is sigma is equal to C into m plus epsilon. All this case epsilon is nothing but the plastic strain, and we know that the total strain consists of elastic strain and plastic strain, and elastic strain because it is very small, you consider it around 0.2 percentage. So, it can be neglected because the plastic deformation, the plastic in case of plastic deformation the strain is very large. So, that you can as a safely ignore those elastic deformation. So, here the C, m and n are constant, n is again the work hardening exponent, okay. C and m are constant. Similarly, OC also has come out with another equation, and then another say Ramberg-Osgood equation. Generally this type of equation is used for fracture studies and other things, and this is also a good form of representing the stress strain curve. So, which is given by strain is equal to sigma by E, where E is the Young's modulus value of the material plus alpha into sigma by sigma naught raised to m minus 1. So, this alpha and m and sigma 0, these are all constant for the material. Now, out of, so and you will find not like this, a large number of forms of empirical equations are available in the literature, okay. But out of all these, the most convenient one expression is that of the Power law equation given in this form, sigma is equal to A epsilon raised to n, because of its simplicity and the way it can be used for any computational purpose. This becomes a very handy relationship, okay. It becomes a very convenient form of convenient relationship for all this analysis purpose. So, where n is the strain hardening exponent and A is the strength coefficient of the material. So, it is basically the strength this strain hardening exponent which decides the material flow of the material, which decides the material flow during the plastic deformation. A, since it is a constant, that is the initial yield stress, normally it will be there or the maximum value. So, this equation, if you take the how to determine A and n, you take the logarithm, so that it can be represented log sigma is equal to log A plus n log epsilon, where epsilon is the plastic strain, and this is of the form of a straight line, the equation for a straight line, y is equal to mx plus c. So, if you take to obtain the value of n and A, what you have to do is that you take the log sigma versus log epsilon plot. From your tensile test data, you find out this log epsilon versus log sigma versus log epsilon, and you will find that it almost fits into a straight line equation. There will be some scatter, but you can get to a very good accuracy, you can get it as a straight line equation, and the slope of this line, because from this relationship slope of the line will give you the n, and the strength coefficient or strain hardening coefficient strength coefficient can be obtained from the fitted straight line. So, where log epsilon is equal to 0. Okay. So, at log epsilon is equal to 0, what is the value of the sigma? So, that value, from that we can find out the value of A. So, log A is equal to log sigma at log epsilon is equal to 0. Okay. So, from that we can find out the value of A and n. So, that is so it is a very simple form of determining these constants. So, the value of strain hardening exponent generally is between 0 and 1. So, 0 means it will be elastic, then 0 means it will be a constant value. It is a perfectly elastic material will be like this, okay, it will remain constant. Now, if it is when n is equal to 1, the material is perfectly elastic, which is in this region, so which you are getting it. So, here it is not deforming plastically. Okay. These are the extreme conditions which generally we will not find it in real materials. The normal value for the n for real materials lies between 0.1 to 0.5. Okay. So, this is the extreme conditions, the limits, but in real material the maximum value you may find is 0.5, maybe some exceptional cases may be there which may go beyond that, but otherwise the value of n lies between 0.1 to 0.5. So, from the definition of n from our previous equation, n is equal to d log sigma by d log epsilon, that is equal to, you can write in this form, log sigma by d log epsilon, that is equal to epsilon by sigma into d sigma by d epsilon. And so, from this relationship we can get that d sigma by d epsilon is equal to n into sigma by epsilon. Now, let us come to the measures of ductility, because for plastic deformation what is important is to how much extent the material can deform. So, that is what is required. So, you may have to conduct this tensile test at various conditions, and ductility, the knowledge about ductility is very important, because all engineering materials for application purpose, especially for structural purpose, it requires some minimum amount of ductility, because you will not use a material which is brittle, okay, because that brittle material will fail without giving any warning, whereas if it is a ductile material, before failure you will get an indication that the material is going to fail. So, for this case, even for when you are going to have plastically deform a material also, you should know to what extent the material can deform. So, that is why we wanted the ductility, the value of the ductility for that material, and from a tension test the ductility generally is to what extent it is elongating before failure. So, this is the extent to which a metal can be deformed without fracture during metal working operation, and it indicates the ability of the metal to flow plastically before fracture, providing a warning before the failure. So, these advantages are there, and it also acts as an indicator for change in the impurity level of processing condition, something which are important for the metallurgist. But as a mechanical engineering, these are the two things two advantages we can have if we know about the ductility. So, about the material ductility, how to measure it? The conventional measurement of ductility of any material, it is by using a tension test or a compression test. For deformation studies, people generally use compression testing, because it is of much more easy, especially when you are carrying out the experiment at a higher temperature, but otherwise at room temperature the data you can have it is from a tension test. These are obtained from the data of the ductility values can be obtained from an engineering strain at a fracture, that is the EF, total engineering strain, and the reduction in the area of fraction, because as we know the deformation which is taking place, it reaches a maximum. Till that time the deformation is homogeneous, and after that the necking starts place, and at the failure strain what is the minimum cross sectional area. So, if you have an idea about the maximum load which it was supporting at the time of failure and the cross sectional area at the time of failure, then you can know what was the stress also which was there. So, this gives the reduction in the cross sectional area, because initially you had a cross sectional area which was A naught, and now you have a cross sectional area A. From that you can find out what is the reduction in the area, cross sectional area at fracture. So, any of these criteria can be used, both are having its own advantages and its own disadvantages. But remember, the engineering strain at fracture EF and the reduction in area at fracture Q, these are being determined from the after fracture of a tensile sample, you join together and across a known distance how much it deforms, that from that you will get this EF. And what was the initial cross sectional area and what is the final cross section at fracture, from that we can find out the reduction in area. So, by definition the fracture strain is equal to L1 minus L naught by L naught into 100. So, into should be there, and the reduction in area is A naught by A1 by A naught into 100. So, from this relationship we can find out that L by L naught is equal to 1 by 1 minus Q, where Q is the reduction in area, cross section area. So, the failure strain, you can find it out is equal to q by 1 minus q. So, you are getting the relationship between this engineering strain and reduction area by this relationship. But before that, I should like to tell you about one thing. Many times the percentage elongation which is given by this relationship EF, when you are quoting that value, you have to mention across what gauge length it has to be there. Either you may tell it was across a 12.5 mm or half inch length or a 1 inch length or maybe 2 inch length. The problem is that necking can take place at any point within that gauge length, or maybe sometimes outside the gauge length, then you are not considering it. Okay. So, when you are keeping a 2 inch specimen gauge length, failure will be taking place, necking will be at some small area only. If it is a 1 inch gauge length, then you will find the total length is reduced. So, if it is a 12 inch gauge length section if you are taking, then you get a much better accuracy. But depending upon the gauge length, your strain value you may get a different value. So, you have to always specify what was the percentage elongation across the gauge length, you have to specify across maybe 25 mm or 1 inch or half inch or 2 inches gauge length you have to tell. Whereas, that is not required when you are going for your reduction cross sectional area, because you are going to get the final cross sectional area, and at that time what was the stress you can get it. So, that is one thing. So, how much the reduction area was there you are calculating. So, this may give a better accuracy, but the difficulty is in conducting the test also. Okay. So, in any case you are going to join together and measure it. So, but in between value you may find it very difficult to get for this, whereas the actual value you may get it for change in length. Reduction in area measurement during the test is very difficult. That is the, so both are having advantages as well as disadvantages. So, the effect of strain rate on the flow properties of the material. So, if you look at the various strain rates which are being used for under different conditions, when the metal is subjected to straining, it is generally done at different strain rates. So, the spectrum of strain rates are, so like you can say that when it is very slow strain rate to the power 10 to the power minus 8 to 10 to the power minus 5 per second, this is something like a creep test. So, in a creep deformation what is happening, that is the strain rate, it is very small. So, like you are subjecting a material to high at an elevated temperature and stresses and keep it for there for a long time, even if it is below the yield strength of the material also, after prolonged exposure, you will find that some amount of deformation is taking place. In normal case, it is not going to affect much, but especially for those materials which are subjected to a higher temperature, this is of more importance. Especially like if you look at the components in a gas turbine blade, or maybe the reformer tube in a chemical industry or a refinery. So, these are subjected to high temperature and some amount of stress, and normally when you do the design of these components, say for example, reformer tube, it is the design life is something around 12 years at that particular temperature and the pressure of application. So, but still you will find that by 12 years, because beyond that you will find that small amount of plastic deformation is taking place. So, that is the case where it is the creep test, that is, so 10 to the power minus 8 to 10 to the power minus 5 per second, that is typical of a creep test, and from 10 to the power minus 5 to 10 to the power 2, it is a typical of a static tension or a compression test, where you are just deforming the material between two jaws, and one is a movable head and another is a fixed head, and then okay, you are just pulling it. So, that normally will be at a somewhat a higher stage, but it is not very high also. So, this 10 to the power 2 is 10 to the power minus 1 it should be. Then 10 to the power minus 1 to 10 to the power 2 is a dynamic tension or compression test, maybe like your fatigue testing and other things when you commit, or maybe your slow impact test, those type things are basically this range will be corresponding to your fatigue testing. Then you have the 10 to the power 2 to 10 to the power 4, the impact testing, HRP, V notch, or an ISO testing, or maybe you find that free falling indentation impact test. So, all those things are coming into picture. So, that will be under that impact testing. Then when you go for very high strain rate, 10 to the power 4 to 10 to the power 8 per second, it is something like explosive forming, okay. Or so those are the, these are the strain spectrum of strain rate which one will be facing in normal engineering applications. And if you look at the flow stress, the dependency of flow stress on the strain rate and temperature, it will show like this. So, you will find that with the increase in strain rate, the flow stress keeps on increasing. That is a trend. Almost with increase in temperature, flow stress keeps on increasing, and with a higher temperature, the slope will be much sharper compared to at a lower temperature. For example, room temperature, you will find that the strain rate dependency on the flow stress is very small. So, your strain rate sensitivity will be very low here, but at elevated temperature you will find that the slope of these curves are changing. So, when the slope is changing, you will find that at a higher temperature, the strain rate is having a higher impact on the flow stress. So, this is what at increasing temperature, the variation of the flow stress will be in this format. Now, effect of temperature on the flow properties, you will see that with the stress strain, typical stress strain curve for a particular strain rate at a constant strain rate, if you look at it, you will find that at higher temperature, okay, this should be the reverse actually. So, it should be so at lower temperature you will find that the stress is increasing for a particular strain, and as the temperature and you have a very less amount of ductility, because the strain till failure is very less. But at a higher when you are increasing the temperature, any engineering material, especially any metallic materials, it is a common sense also that if you heat it, it becomes much more soft. Okay, and you can easily deform the material if it is heated. Otherwise, no, 1 or 2 times, no, you heat it, no, you bend it, then it gets hardened and it becomes very brittle. So, this is a very it's a layman will understand these things. So, that means with increase in the temperature, you will find that the ductility is increasing, and that increase in the ductility is very high, but at the same time the yield strength or the flow behavior of the material will be lower than that corresponding to at a higher temperature. So, this is the general flow behavior at higher temperature. So, with this now during this test we should have some idea, like if the test is carried out at a high speed or high strain rate at a high rate, then you may get a different value, especially that is of importance when the tests are carried out at a higher temperature, at elevated temperature. So, there is the total, the flow stress which you are going to get, it depends upon the strain, the rate at which it is strained, and the temperature at which the test has been carried out. So, the flow stress is a function of stress, strain, strain rate and temperature. So, you have to know about the effect of strain rate on the flow properties of the material. So, if you are carrying out at different temperatures, and now the strain rate, it is expressed by this rate of strain, that is epsilon dot is nothing but is equal to d epsilon by dt, and is expressed in terms of per second. So, when you look at the spectrum of strain rate, so this data is taken from say G. Dieter, the mechanical metallurgy. So, the range of strain rate, you will see that from 10 to the power minus 8 to 10 to the power minus 5 per second, then it will be something like which is equal to a creep testing, where the deformation rate is very small. Okay. So, it may take several years to have say a small amount of strain. So, that corresponds to a creep testing or creep phenomena. But if the strain rate is varying from 10 to the power minus 1 to 10 to the power 2 per second, it corresponds to a static tension or a static compression test, which you always do it under a static machine. Just loading it so that it is strained and measure the load versus the specimen gauge length extension. So, that is a it corresponds to a static tension test condition or a static compression test condition. Now, if the strain rate varies from say if it is increasing, it corresponds to dynamic tension compression test, and with the further increase it corresponds to impact test, and with a very high strain rate it is explosive forming. So, there is this negative signs and these values have come, there is a mistake has come, and I am very sorry that I will correct it next day. But if you look at when the experiments are carried out at different temperatures and at a constant strain rates, we will come to that how it is conducted. The flow stress values, you will find that you are getting the curve like this with increasing temperature coming down, you will find that the flow curve keeps on decreasing, and with the strain rate increasing, you will find the flow stress keeps on increasing. So, this is the case, the individual cases done carried out at different temperatures, and so with increase in temperature the flow stress value decreases, with increase in strain rate the flow stress value increases. How to express or how to carry out a test by means of constant strain rate? So, two types of strain rates are there. One is by using either the conventional linear strain or true, or the second case is by considering the true strain. Okay. So, when you are taking the considering the conventional linear strain, then we say that this an experiment can be carried out under a tensile testing machine in a tensile mode or in a compression mode. Okay. So, for the case of extension of a cylindrical specimen with one end fixed, most of these machines you will find that one end of the crosset is fixed and the other will be moving, and the specimen is clamped into that. So, maybe the top one may move or the bottom one may move. In any case, the load is applied and there will be a load cell to measure the load which is coming during the extension. Okay. So, if the crosset is moving with if the movable crosset is moving with a velocity v, then we can say v is equal to dl by dt, okay, where L is the change in length of the specimen, that is correspond to how much it is moving. So, conventional strain rate can be calculated by this relationship E dot is equal to dE by det, that is nothing but d by dt of L minus L naught by L, where L is the instantaneous value. Okay. So, that we can get it as 1 by L naught into dL by dt, L minus L naught by L naught here. Okay. So, that is equal to 1 by L naught into dL by dt, that is equal to V by L naught. So, in the conventional strain rate, when you are looking at it, you are considering only the initial gauge length and your velocity is constant. So, when you are doing this experiment at a constant crosset velocity, your engineering a conventional strain rate remains constant, or engineering strain rate remains constant. Okay. But your true strain rate is not constant. The conventional strain rate is proportional to crosset velocity v. In conventional testing machine, it is possible to carry out at a test at a constant strain rate only, constant engineering strain or conventional strain rate only. You cannot carry out a test at a constant true strain rate testing. So, for true strain rate, it is defined by say epsilon dot is equal to d epsilon by dt, that is by epsilon you can say d into log L by L naught by dt, which implies that epsilon dot can be obtained by this relationship with the V by L. So, if you compare with the previous equation, that is epsilon dot is equal to V by L and E dot, your conventional strain rate is equal to V by L naught. So, here for carrying out an experiment at a constant strain rate, if it is a tensile specimen, when the gauge length increases, you will see that your strain rate has to, your velocity of the crosset has to change. So, by conventional static machine this is not possible. So, when you wanted to carry out an experiment using an experiment with a true strain rate test, constant true strain rate test, you need to have a machine with a feedback control system. So, that as the specimen gauge specimen length gauge length changes, your velocity has to change. So, that is what. So, this The relationship between true strain rate and conventional strain rate also can be obtained by this relationship, that is epsilon dot is equal to V by L, that is equal to L by L naught into dE by dt, because dE by dt you can get it, and that is equal to 1 by 1 plus E into dE by dt. Okay. So, this you can get it from this relationship. So, you will find that ultimately, because V is equal to L naught into dE by dt, that is what you are getting. So, epsilon dot is equal to E dot by 1 by epsilon dot. So, from the previous, as I was telling, the true strain rate will decrease as the specimen elongates when deformed at a constant Crossett velocity. A machine with an open loop control is necessary to maintain a constant true strain rate testing during the test, such that the Crossett velocity increases as the specimen elongates. At initial stages, there were equipments where it was mechanically designed so that for a constant you are able to get a constant strain rate testing also, but nowadays now with advanced electronic systems and microprocessor system, this with open loop controls machines are very easily available everywhere. So, nowadays people follow that one. So, since the for a constant strain rate testing, if you wanted to carry out, the Crossett velocity will vary. This by a simple derivation you can get this of this form, where velocity with respect to time is obtained by this constant velocity into L naught into exponential epsilon naught t. From that relationship we can always get with the time how the velocity should change. So, you can always allow your Crossett displacement accordingly moving. The general relationship between sigma, the flow stress and strain rate at constant strain is of the form sigma is equal to C into epsilon dot raised to the power m at a constant strain and temperature. So, where m is called as the strain rate sensitivity. Okay. So, this similar to our previous equation for sigma versus so you are getting the Hollow mount relationship. In the similar way you can find out, but the experiment has to be done at a constant strain rate and constant strain and constant so at a constant value of strain and temperature if you take it, and then from that now you can find out, you do it at a different strain rate and then find out the value of sigma for a constant strain and temperature, and from that value you can always find out. So, you plot a log sigma versus log epsilon dot plot for a constant strain value and at a constant temperature, and from that we can get it. By m can be obtained by carrying out test at different true strain rates epsilon dot 1 and epsilon dot 2 and finding out the corresponding flow stress values sigma 1 and sigma 2 at any constant strain and a constant temperature. Another convenient, because this takes lot of time, especially when you are carrying out a test at very slow strain rate test. When you are doing it, one test itself will take lot of time. So, to save the time, people also carry out that in a single specimen you do a rate change test, strain rate change test you do. You are initially doing an experiment at a constant strain rate epsilon dot 1 with your feedback control machine, and when it reaches a constant value of say maybe some strain, then suddenly you jump the strain rate. Nowadays, no, that is very, it can be done very easily in the machine with the microprocessor control. So, you from epsilon dot 1 to another strain rate epsilon dot 2, you suddenly have a jump. So, when that is done, you will find that when the strain rate is higher, if strain rate epsilon dot 2 is higher than epsilon dot 1, you will find that the flow stress increases, or if it is reduced, flow stress will reduce. So, and then you carry out the experiment for some more strain and then suddenly come back to the initial stage. So, if you are carrying out the experiment at this strain rate, it would have followed like this curve. So, now you know that epsilon 2 and epsilon sigma 2 and sigma 1 corresponding to epsilon dot 1 and epsilon dot 2 and epsilon dot 1. From this value you can always calculate, even maybe for this strain you can find out, in this case we can find out for the different strain value, and that you can get it by the basic definition m is equal to del log sigma by del log epsilon dot at a constant strain and temperature. So, that you can get it in this form epsilon dot by sigma into d sigma by d epsilon del sigma by del epsilon. So, you can get it in this differential form, and from finally you can arrive that m is nothing but log sigma 2 by sigma 1 divided by log epsilon dot 2 by epsilon dot 1. So, sigma 2 is known, sigma 1 is known, epsilon dot 1 and epsilon dot 2 is known. So, for a particular strain you get it. So, for two strains also, one strain here, one strain corresponding to here, you can get it. So, you can find out the value of the strain rate sensitivity of the material. And you may please note that the value of m for metals, it is almost 0, it is much less than 0.1 at room temperature. When you are doing it at room temperature, it is not showing much influence on the strain rate, it remains almost constant. But the situation is complicated when you are doing, especially at a hot working condition, at a higher temperature when you are doing it, especially for a hot working condition where the flow stresses will be lower. In that condition, you will find that you are having an appreciable amount of value of m. The m increases with the temperature, especially above a homologous temperature of 0.5. That means 0.5 means in the absolute scale, when the temperature is more than half of its absolute temperature, you will find that the strain rate sensitivity comes into picture. So, there the flow stress will be heavily dependent upon the temperature dependent upon the strain rate which we are doing. Okay. So, for hot working condition, m values of 0.1 to 0.2 are very common for most of the materials. Now, high strain rate sensitivity, that is high value of m, is characteristics of superplastic metals and alloys. So, metals, there are certain materials which can be deformed under superplastic condition. That means the elongation which you can get is extremely very large, maybe 100 or 1000 times of the gauge length. So, it is a typical example is that you take a glass rod, heat it. So, in this case, when there is a superplastic deformation, the necking, phenomena of necking is not taking place. Okay. And at that condition, under certain conditions only you can carry out that. Under that condition, you will find that the flow stress is very, very less than 1/10 or 1/15 of the actual case at room temperature. So, you may be able to deform even a ceramic materials at a higher temperature at a flow stress of even maybe 10 or 12 megapascal. So, that is the beauty of this superplastic deformation. Okay. So, there under those certain conditions you can deform it to a very high amount of strain, maybe 100, 500 or 1000 or even 5000 percentage depending upon the material. So, the percentage elongation will be so high, and the material then deforms under that conditions at a very low flow stress value. The main conditions for superplastic deformations which people have highlighted, but there are some exceptions also, are that it should consist, the grain size of the material should be very fine, that means it should be below 5 micrometer, and it should consist of two phases. One should be a brittle phase and which is discontinuous, and the other is a ductile phase which is a continuous phase. Okay. But in some cases this may not be necessary, but in general metallic materials these are necessary. Okay. And the material should have a very high value of strain rate sensitivity index, that is the m value should be more than 0.5, and the strain rate should be very, very small. At a very high strain rate it may not work out. So, strain rate has to be very small. So, in that case you can deform the material without any type of necking. So, localized reduction and cross section will not be taking place, and you can get some very particular shape inside a die if you do it with air pressure or hydrostatic pressure. If you are doing it, or with air pressure, compressed air pressure at a higher temperature, if you do it, the material will deform in a homogeneous way, and with a uniform thickness we can get it any complicated shapes we can be it can be obtained. So, that is the advantage. Even ceramic materials can be deformed by super, not all, but certain ceramic materials also can be subjected to superplastic deformation. And if you look at the effect of temperature and flow properties, the strength decreases and ductility of the material increases as the test temperature is increased. This behavior may be altered. This is under normal condition if there are structural changes taking place. So, like precipitation phenomena, in a precipitation hardenable alloy, if very fine precipitates are nucleating and growing from the matrix, from a supersaturated matrix, then this behavior may change. Sometimes instead of decreasing the strength, you may end up with increasing the strength, okay? And like a strain aging if it is taking place. So, that means if it is done at a very low, at a slow rate, sometimes yield strength may again come back and other things. So, strain aging also if it is taking, or maybe recrystallization taking place. When the recrystallization taking place, then okay, ductility may be, you can have a very high amount of ductility, especially at a lower temperature and other things compared to that. So, that means, so all these metallurgical phenomena if it is taking place, then okay, there will be a deviation from this case. This is a general trend. Sometimes you may find that phase transformation is taking place. Then also you will find that okay, it may not be following this trend, but in the same domain where the structural changes are not taking place, where it is a constant structure is obtained and there is no microstructural changes and other phenomena like recrystallization and other things are not taking place, then you will find that the strength decreases and ductility of the material increases with increase in the temperature. So, you can say that most of this thermally affected phenomena, especially when you go to a higher temperature, the thermally activated phenomena that assist the deformation and reduces the strength at higher temperature, because that also comes into picture. One thing is that with increase in temperature, okay, softening is taking place. Another is that thermally assisted phenomena takes place. Okay. So, for so you have something called as the activation energy for the plastic deformation. So, you will find that based on that the yield strength or the flow stress can be represented in this form C2, which is a constant, into exponential minus Q by RT. So, that is at a constant stress and strain rate. So, you will find that the temperature dependence on the flow stress is there. So, this Q you can obtain by plotting from these different values. Now, you plotting the log sigma versus 1 by T. Sometimes people say it is 1000 by T also. So, in one whatever it be, it is at the log sigma versus 1 by T data. If you just plot it, it will almost be a straight line, and then you take the slope of that curve, that will give you the value of Q by T. So, from that, depending upon the temperature, you can calculate the activation energy for the plastic flow for the material.